On August 27, 1883, Krakatoa made the loudest sound in history, and the pressure wave that carried it circled Earth 3.5 times. A barograph at the Batavia gasworks, 100 miles from the volcano, recorded a pressure spike of 2.5 inches of mercury. Converted into a sound pressure level, that reading is 172 decibels. The human pain threshold sits at 130 decibels, and a jet engine at takeoff hits about 150. The wave passing through Batavia that morning was much louder than a jet engine. It had already traveled 100 miles to get there. 3,000 miles further out sits a British colonial outpost called Rodrigues Island. The chief of police there logged the sound that morning as the distant roar of heavy guns. The roar had just crossed the entire width of the Indian Ocean to reach his copper-roofed police shed. It still arrived loud enough to be mistaken for naval artillery firing nearby. Symons was the British meteorologist who compiled the Royal Society's 1888 report on the eruption. He collected sound reports for more than 50 stations across the globe. A man in Perth, Australia, 2,000 miles from the strait, reported the noise woke him at 4 in the morning. He thought a battleship had opened fire offshore. A police officer in Diego Garcia, in the central Indian Ocean, logged distant cannon fire on the same night. None of these witnesses were anywhere near a battle. The audible footprint covered roughly 13% of the planet's surface area, which remains the largest single-event sound footprint ever recorded. You've read that the sound at the source measured 310 decibels. The 310 decibel number is wrong in a useful way. Real sound waves can't exceed 194 decibels in Earth's atmosphere. At that level, the pressure swing of the wave equals 1 full atmosphere of variation. Air molecules can't be pulled into rarefaction beyond a vacuum. Above 194 decibels, the wave stops behaving like sound and starts behaving like a shock wave. A shock wave is a propagating pressure discontinuity that compresses everything in its path. The 310 figure is what the radiated acoustic energy would have measured if sound were physically allowed at that level, but it isn't. So what actually traveled outward from Krakatoa was a shock-wave pressure pulse hybrid. The hybrid was still 172 decibels when it reached cities 100 miles away. The total energy released has been estimated at 200 megatons of high explosive, which is roughly 840 petajoules. That figure is about 4 times the yield of the Tsar Bomba, the largest man-made thermonuclear weapon ever detonated by any nation. A single Krakatoa explosion outranked the largest man-made detonation in history by a factor of 4. The volcano did it from a chamber of magma in the Sunda Strait, not from a Soviet test pad in the Arctic. The reason that much magma was waiting under Krakatoa comes down to plate tectonics. The Sunda Strait sits on the Sunda Arc. It's the volcanic chain formed where the Indo-Australian plate dives beneath the Eurasian plate at about 70 millimeters per year. The descending oceanic slab drags water down with it. At depths of 100 to 120 kilometers, that water gets squeezed out of the mineral crystals it was bound to. The water then rises into the hot rock above the slab. Water lowers the melting point of mantle rock, so the rock starts to melt. The melt is silica-rich, which means it's also gas-rich and viscous. Silica-rich magma traps dissolved gas the way a shaken soda bottle traps carbon dioxide. When the pressure cap finally fails, the gas comes out catastrophically. Krakatoa was a gas-rich, silica-rich magma chamber with a thin volcanic edifice on top. It sat in the most active subduction zone on the planet. Barographs everywhere on Earth recorded the pressure wave passing 7 times over 5 days. There were 4 outbound passages from Krakatoa toward the antipodal point in Colombia and 3 return passages back toward Indonesia. The atmospheric phase velocity of the wave is now a measurable constant. Physicists call it the Lamb wave speed, about 1,086 kilometers per hour. A Lamb wave is a specific kind of guided atmospheric wave. It travels horizontally without dispersing because the atmosphere acts like a thin wave guide between the ground and the upper layers. The wave doesn't shed energy upward the way ordinary sound does. That's why a single 1883 event left a detectable signal on barographs for 5 days. The wave kept bouncing between Krakatoa and its antipode for the rest of the week. The 2022 Hunga Tonga eruption in the South Pacific gave physicists a chance to revalidate Symons' 1888 barograph analysis. A team of 76 scientists from 17 nations published the Hunga Tonga atmospheric wave dataset in Science. The Lam wave from Hunga Tonga circled Earth 4 times and matched the Krakatoa wave amplitude almost exactly. The Hunga event also pushed measurable disturbances into the ionosphere 100 kilometers up. It generated infrasound at frequencies humans can't hear. The audible part of the sound reached up to 10,000 kilometers from the source. Symons couldn't measure most of that in 1883 because the instruments didn't exist. The modern dataset proves he interpreted his barograph traces correctly anyway. Here's the part nobody who heard the sound understood at the time. The sound itself wasn't what killed most of the people who died that day.
At 2 minutes past 10 in the morning, the third and largest of the 4 main explosions occurred. The first happened at 5:30 at the Perbua-Watan vent, the second at 6:44 at the Danan vent. The third explosion destroyed the island. About 21 cubic kilometers of rock, magma, and pumice were ejected into the atmosphere. The remaining edifice of Krakatoa collapsed downward into the emptied magma chamber. A caldera, roughly 6 kilometers across, opened where the island had been. The seafloor dropped from a depth of 100 meters to a depth of 200 to 300 meters within minutes. For 100 years, geologists thought the collapse of that caldera generated the tsunami. The collapse hypothesis fails on the timing. A 2011 study by Maeno-Imamura at Tohoku University ran the fluid dynamics. The waves that hit the Sunda Strait coastline aren't consistent with caldera-collapse generation. They're consistent with a pyroclastic-flow. The flow slid off the eruption column and entered the sea at a discharge rate above 10 million cubic meters per second. The volume of solid material exceeded 5 cubic kilometers. The pyroclastic flow carried temperatures around 700 degrees Celsius and traveled at velocities near 100 meters per second. When that flow hit cold seawater, the water at the contact surface flash vaporized. Flash vaporization produced a steam-driven explosion underneath the leading edge of the flow. The steam lifted the hot cloud off the ocean surface and let it skim across the strait like a hovercraft built out of incandescent ash. Carey and Sigurdsson mapped the deposits in 1996. They found Krakatoa pyroclastic flow material on islands more than 80 kilometers from the source. The mechanism explains the tsunami and the burn injuries on survivors found far from Krakatoa. In the town of Murak, on the Java side of the strait, the tsunami run-up reached 46 meters, or 151 feet. The run-up was higher than most 8-story buildings. Along the rest of Java's western coast, the waves averaged 42 meters, 138 feet tall. The villages of Anjer and Schuringen were erased within 90 seconds of impact. The Dutch colonial gunboat Barau was carried 3.3 kilometers inland. The wave dropped the gunboat in a jungle clearing 30 feet above sea level, with all 28 crew dead. 2 years later, the Dutch geologist Verbeek compiled the official body count and recorded 36,417 deaths. Modern historians estimate the actual toll exceeded 120,000. Verbeek's census missed the coastal Sundanese villages that had no Dutch colonial registry to count from in the first place. The waves also showed up as pressure-correlated oscillations on tide gauges as far away as the English Channel. The gauges measured a few centimeters of sea level disturbance, 12,000 kilometers from the volcano. The disturbance arrived faster than ordinary tsunami physics would predict. Modern reanalysis credits the same Lam wave that registered on barographs. The wave carried part of the tsunami signal through the atmosphere, depressing the sea surface as it passed overhead. But the 1883 Krakatoa story doesn't end at the coastline. It doesn't even end on the planet's surface. The third explosion injected somewhere between 20 and 50 megatons of sulfur dioxide gas into the stratosphere. The stratosphere is the layer of atmosphere between 20 and 50 kilometers up. Sulfur dioxide reacts with water vapor at that altitude to form sulfuric acid aerosol droplets. The droplets are microscopic, and they reflect incoming sunlight back into space without warming the air around them. Because Krakatoa sits within 5 degrees of the equator, the aerosol veil spread north and south along the global stratospheric circulation. By December 1883, the veil was global, and the Northern Hemisphere summer temperatures dropped by 0.4 degrees Celsius the following year. A measurable climate signal persisted for 4 to 5 years. The popular claim of 1.2-degree global drop is wrong, and the 2020 Schurer reanalysis puts the actual drop at 0.4 degrees. But 0.4 degrees worldwide for half a decade was still enough to redden every twilight on the planet for 2 years. The chemistry of those red afterglows is specific to the droplet size. Sulfuric acid aerosols at 25 kilometers altitude form droplets with a typical radius of about half a micrometer. That radius is on the same order as the wavelength of visible light. The size puts the scattering into the Mie regime rather than the Rayleigh regime. Mie scattering off droplets of that size class scatters blue light forward and red light back toward the observer. The result was a series of post-sunset afterglows that newspapers across Europe and North America described as fires in the sky. Fire brigades from Connecticut to New York actually responded to those afterglows as real fires before figuring out the sky itself was glowing. In late November 1883, the Norwegian painter Edvard Munch was walking along the Liabra-Hausea road overlooking Christiania Harbor. He looked southwest, the exact direction from which the Krakatoa afterglows appeared in Norway that winter. He wrote in his journal that the sky turned blood red and tongues of fire hung above the city. A decade later, he painted the memory, and the result was the scream. In 2004, a Texas State University astronomy team led by Donald Olson mapped the exact location Munch was standing. They confirmed it matched the documented Krakatoa twilight pattern. A 2018 Bulletin of the American Meteorological Society paper argues Munch was depicting mother-of-pearl clouds instead. Those are high-altitude polar cloud type, sometimes visible from southern Norway. The Olson interpretation remains the most widely cited.
The Krakatoa caldera didn't stay empty for long. A new volcanic cone began rising from the seafloor inside the caldera in the late 1920s, decades after the eruption. Indonesians named the new island Anak Krakatau, the child of Krakatoa. By the 2010s, Anak Krakatau stood several hundred meters above sea level, on the same magma supply line that had powered the 1883 catastrophe. On December 22, 2018, less than 0.2 cubic kilometers of the southwestern flank of Anak Krakatau collapsed during an eruption. The 2018 flank collapse was tiny compared to the 1883 caldera collapse, less than 4% of the volume the 1883 event produced. The collapse still generated a tsunami that killed 437 people along the Sunda Strait coastlines, and the modern tsunami warning system missed it entirely. The Grilli team at the University of Rhode Island reconstructed the collapse using satellite radar and seismic data. They concluded the failure was driven by slow gravitational sliding on a dipping décalon inside the volcano. The sliding produced almost no high-frequency seismic energy. High-frequency seismic energy is what the global tsunami warning network listens for. The slope quietly let go in the middle of an active eruption. The collapsed material dropped into the sea and built a 15-foot wave that hit shore before any warning got issued. The same mechanism Maeno-Imamura proposed for the 1883 tsunami killed people again in 2018. Pyroclastic and gravitational displacement of seawater, not tectonic faulting.
The Sunda Strait remains the most observed volcanic crisis zone on Earth. The 2018 event proved a hard point about how little the warning systems have caught up. Even with modern instrumentation, the network still can't see the failure mode that killed 36,000 people in 1883. If the physics here hooks you, the Mount St. Helens story will hit you the same way. Same forensic case, different angle. And that video is right here on Sketchy Science.